All right, let's jump into a deep dive today that's maybe a bit different. We're not looking at brand new research, but a real classic. George Gamow's 1, 2, 3, Infinity, Facts and Speculations of Science.
Oh, yeah. This book, originally from 47, revised in 61, it's really remarkable. Gamow was, well, a brilliant physicist, and his goal here was pretty ambitious to give readers this sweeping picture of the universe,
Covering everything.
everything from the tiniest subatomic particles to the absolute vastness of space and time, the microscopic and macroscopic manifestations, as he called it in the preface.
So our mission in this deep dive is, well, to guide you through some of the most surprising facts and fascinating ideas Gamow unpacked in this book.
Yeah, we'll explore his take on things like mind-bending numbers, the nature of infinity.
The strange geometry of space-time, the building blocks of matter. It's a chance to see the universe through the eyes of, like, a master science communicator from a really pivotal era in physics.
Absolutely. It's
Yeah.
going to be fun.
Okay, let's get started. And where do we begin? With something that seems so simple. Numbers. Specifically, how high can you really count?
Right. Gamow opens with this amusing story. He calls it a malicious slander, but it makes a point about these two uh, Hungarian aristocrats.
Yeah.
One challenges the other, name the biggest number you can think of. After ages, the first guy says 3.
3.
That's it. Well, yeah. And
Oh.
then after a long pause, the second one says, you win.
Huh? Okay, that's ridiculous.
It sounds silly to us now, right? But it gets at a fundamental challenge. Without a good system to write numbers down, our ability to handle big quantities as well, it's super limited.
Yeah, imagine being an ancient Roman trying to write 1 million. The source mentions it would take up a whole wall with their numerals.
Exactly. Their system just wasn't built for really, really large numbers.
So writing them became crucial. And this is where someone like Archimedes, way back in the 3rd century BC, made this like giant leap.
Yeah, in his work, The Samites, or Sand Reckoner, he basically set out to prove you could express numbers that seemed totally inconceivable.
Like the number of grains of sand to fill the universe.
Exactly. The universe as they understood it then, which was maybe a sphere 10 billion miles across. He didn't just say it's a big number.
He figured out how to write it.
He invented a system using myriads, which is 10 to the 8, as a base unit, and then creating orders based on that. He could get up to octades 10 to the power of 64.
Wow.
The insight there isn't just the number itself, it's that he devised a systematic way to represent that kind of unimaginable scale, mathematically.
Okay, let's look at another classic story about huge numbers, this one from Doubling. You probably know the legend, right? The Grand Vizier Sissa Benda here, inventing chess.
Oh, the chessboard and the wheat. Yeah. The king offers any reward, and Sissa asks for 1 grain of wheat on the first square, 2 on the second, 4 on the third, doubling each time.
Seems humble at first.
Deceptively so. It's a geometric progression, and those numbers, they just explode. By the 64th square alone, you're talking 2 to the power of 63 grains.
And the total.
The total is 2 to the power of 64 minus 1. That's over 18 quintillion.
18 quintillion.
Yeah, 18,446,744,709,551,615 grains. The takeaway here is just how fast exponential growth totally blows past our intuition about scale.
It's not just big, it's a demonstration of how simple rules generate quantities beyond comprehension.
And Gamow links this to that mythical Tower of Brahma puzzle, the one with the monks moving discs?
Yeah, the same number of moves needed, right?
Exactly. And if they moved 1 disc per second, it would take over 58,000 billion years.
1,000 billion years. That's insane.
Compare that to the age of the universe estimates back when Gamow was writing. The first edition said maybe 2 or 3 billion years. The 61 update upped it to 5 billion or more.
Even the sun's estimated lifespan was only 10-15 billion years.
Right. Even a legendary universe age linked to the story was just over 20 billion. The Tower of Brahma timescale is just vastly, almost absurdly longer than the perceived age of reality itself back then. It really shows how these combinatorial numbers just skyrocket.
Here's another one from the book that kind of blew my mind. The problem of a printed line. Imagine like an automatic printing press just churning out random combinations of letters and symbols.
Yeah.
Say we use 26 letters and 14 symbols, so 50 possible characters.
Yeah.
For a line of just 65 characters, how many unique combinations are there?
Oh, it's going to be big. It's 50 raised to the power of 65, which is, let me think, about 1 followed by 110 zeros. 10 to the 110th power.
You can't even really say that number.
Right. And Gamow imagines this machine just printing nonstop for billions of years. The key insight, the really wild part, is that somewhere in that unimaginable mess of random print,
You'd find everything.
everything, every possible sequence of 65 characters, every book ever written, every poem, every conversation like this one, future scientific papers, it's all in there somewhere, surrounded by just oceans of complete nonsense.
That powerfully illustrates the sheer scale of possibilities, doesn't it?
Yeah.
How chance, given enough time and space, could stumble on meaning.
Exactly. It's staggering.
So, okay, we've talked about incredibly large, but still finite numbers.
Yeah.
But what about numbers that are truly infinite? Can we even compare infinities? That sounds impossible.
Well, this is where George Cantor comes in, and his work was, frankly, revolutionary. He showed that infinities aren't all the same size.
How do you measure infinity?
He developed this method called one-to-one correspondence. Basically, if you can pair up every element in one infinite set with every element in another infinite set with none left over in either.
Then they're the same size infinity.
Exactly. The infinities are the same size or the same cardinality, technically.
Okay, give me an example. Something surprising.
Okay, here's a classic one from the book. Compare the set of all even numbers with the set of all integers, positive, negative, 0. Intuitively, you'd think there are fewer even numbers, right? Half as many.
Yeah, definitely. Seems obvious.
But using Cantor's method, you compare one integer with 2 even, 2 with 4, 3 with 6. You pair every integer n with the even number 2. You can always find a unique even number for every single integer.
Wait, so you're saying the infinity of even numbers is the same size as the infinity of all integers?
Yeah.
Even though it looks like a part of it.
Precisely. That's one of the first really weird paradoxical insights you get with infinite sets. A part can be equal to the whole when infinity is involved.
Huh.
Gamow illustrates this brilliantly with Hilbert's hotel. You know, the infinite hotel.
Vaguely. Infinite rooms, right?
Infinite rooms, all occupied. A new guest arrives. What does the manager do?
No? Tell them there's no vacancy.
Nope. The manager tells the guest in room 1 to move to room 2, guest in 2 to move to 3, guest in n to move to n plus 1, all the way down the infinite line.
So room 1 becomes free.
Exactly. An infinite hotel always has room, even if it's full. You can even accommodate an infinite number of new guests. It shows how infinity behaves differently from finite quantities.
My brain hurts a little. And it turns out the infinity of fractions, rational numbers, is also the same size as the integers?
Yep. Using a clever way to arrange all fractions in a list, you can show there's a one-to-one correspondence. So integers, even numbers, odd numbers, fractions, they all belong to this first sort of smallest level of infinity. Cantor called it Aleph-0, written N0.
Okay, Aleph-0. But here's where I think it gets really interesting and maybe even more counterintuitive. What about the number of points on a continuous line, including all the irrational numbers, the decimals that go on forever without repeating, like pi or the square root of 2. Is that infinity the same size as Aleph-0?
This is Cantor's biggest discovery in this area. The infinity of points on a line, the real numbers, is larger than the infinity of integers or fractions. It's a whole different level of infinity.
Bigger. How did he prove that?
Yeah, with his famous diagonal argument. It's ingenious, really. The basic idea is, imagine you could somehow make an infinite list of all the decimal numbers between, say, 0 and 1, even if your list is infinitely long.
You can still find one you missed.
You can always construct a new decimal number that is guaranteed not to be on your list.
Oh, how do you do that?
You look down the diagonal of your infinite list. Take the first decimal digit of the first number, the second digit of the second number, the third of the third, and so on. Then you create a new number by changing each of those diagonal digits.
Oh, I see. Like, if the first digit on the diagonal is a 3, you make your new number's first digit a 4. If the second is a 7, make yours an 8.
Exactly. The new number you build will be different from the first number on the list because the first digit is different from the second number, second digit is different from every number on your supposedly complete list in at least one place.
Which means your list wasn't complete after all. You can always find one you missed. That's incredible.
It really is, and it proves decisively that the infinity of real numbers, points on a line, is fundamentally bigger, a higher order of infinity than the countable infinity of integers or fractions.
So that's a different Aleph number.
Right. Gamow introduces the notation for this larger infinity, Aleph-1, N1. And interestingly, the infinity of points inside a square or even inside a cube is also Aleph-1.
Wait, the points in a whole cube is the same infinity as the points on just a line segment?
Yep. another weird property of infinity. And Gamow even mentions LF2, N2, for the infinity of all possible geometrical curves.
And he concludes that, based on the science back then, these first three infinite numbers were enough to count anything we can think of.
Wow.
What a trip through different sizes of infinity.
Absolutely. And, moving on from just the quantity of numbers, Gamow also dives into different kinds of number.
Like prime numbers.
Yeah, he touches on primes, those numbers divisible only by one in themselves, like 2, 3, 5, 7. And he mentions some famous unsolved problems related to them, like the Goldbach conjecture. The idea that every even number greater than 2 can be written as the sum of two prime numbers. It sounds simple, it's been checked for enormous numbers, but still, no one's actually proven it's always true.
Huh. Still unsolved.
Still unsolved. He also briefly mentions Fermat's great theorem, which was famously unproven for centuries until Andrew Wiles solved it much later in the context of primes and things like Pythagorean triples.
The 3.4.5 triangle thing.
Right, the Egyptian triangle. These are all natural numbers or relationships between them. But then there's this whole other class of numbers that, well, mathematicians initially thought were just made up. Artificial.
Okay, let's unpack this. You mean the square root of negative numbers?
Exactly. Taking the square root of, say, metric 1 just didn't seem to correspond to anything real. For centuries, mathematicians like Cardan, back in the 16th century, and later Euler, they'd run into these things in their calculations.
So they just ignored them or called them names.
Pretty much. They called them imaginary or meaningless because they didn't seem to represent any actual quantity you could measure.
But they kept cropping up.
They did. And mathematicians found that if you just accepted this unit I, where I squared equals mitre 1, you could build a consistent, logical mathematical system. And when you combine these imaginary numbers with ordinary real numbers to make complex numbers like a plus bi, they turned out to have surprising mathematical power.
And the book gives that fantastic treasure hunt example, right? To show they're actually useful.
Oh, yeah. The island treasure hunt, figure 11. It's brilliant. You've got a gallows, an oak tree, and a pine tree on an island.
Right, and the instructions involve walking from the gallows to the oak, turning 90 degrees right, walking the same distance, marking spot 1.
Then back to the gallows, walk to the pine, turn 90 degrees left, same distance, mark spot 2. The treasure is halfway between spot 1 and spot 2.
Okay, so it sounds like you absolutely need to know where the gallows are to find the treasure.
That's what you'd think. But the amazing insight Gamow shows, using complex numbers to represent the locations and the turns.
The turns are like multiplying by I.
Yeah. Multiplying by I for one turn and I for the other. When you do the math to find the midpoint between spot 1 and spot 2, the term representing the gallows position completely cancels out.
No way. So the treasure's location doesn't depend on where the gallows were at all.
Not one bit. It's this incredible aha moment. These numbers, initially dismissed as purely imaginary, turn out to have a concrete application in geometry and navigation. It shows how abstract math can just unexpectedly connect right back to the real world.
That is cool. A really beautiful demonstration.
Isn't it?
Okay, so speaking of space and geometry, let's shift from the properties of numbers to the unusual properties of space itself. Gamow kicks this off with basic stuff, right? Like Euler's theorem for polyhedrons.
Yeah, VE plus F equals 2. The number of vertices, corners, minus the number of edges plus the number of faces always equals 2. For simple shapes like cubes or pyramids, it works perfectly.
A simple formula, but it leads somewhere deeper.
It does. It's actually a gateway into topology. The core idea of topology is studying properties of shapes that don't change even if you stretch or bend them, as long as you don't tear holes or glue bits together. Euler's VE plus F2 holds for any shape that's topologically like a sphere, basically, a solid lump with no holes through it.
But what happens if the shape does have a hole, like a donut?
Then the formula changes. As the book shows, for a shape with one hole, like a donut or a torus, VE plus F equals 0. For a shape with two holes, it's minus 2. The number of holes, the genus, is a fundamental topological property. The insight here is that the structure of space, or an object, isn't just about distances and angles, it's also about its fundamental connectivity. Does it have holes?
Tautology is like rubber sheet geometry. It cares about holes, not lengths.
That's a great way to put it. Gamow also mentions the famous four-color problem here.
Oh yeah, coloring maps.
The idea that any map on a flat plane or a sphere can be colored with just 4 colors, so no neighboring regions share the same color, seems simple, but proving it mathematically was incredibly hard, another topological puzzle.
And the book then starts hinting at even weirder possibilities for space itself on a huge scale.
Exactly. Using analogies like squishing a dented shape into a smooth one without changing its basic structure, it suggests that our familiar 3D space might not just go on forever in straight
It
lines.
could curve back on itself.
It could potentially be self-enclosed or closed upon itself at cosmological distances. It might have no edge or boundary, but still be finite in volume because of an overall curvature.
Mind-bending stuff.
And then we get to surfaces with truly bizarre properties, like the Mobius strip.
The one-sided strip.
Right. We live in a world where things usually have two sides, inside, outside, top, bottom. But a Mobius strip, made by giving a paper strip a half twist before joining the ends. It only has one side and one continuous edge.
I remember making those.
Yeah.
Still seems weird.
It is. Gamow uses that fun analogy of a donkey walking along it. If it starts on the outside, facing one way after one full lap, it ends up back at the start.
But facing the opposite direction.
Exactly. Its left profile becomes its right profile. The insight is that moving on such a surface can fundamentally mess with your orientation. Could our universe have similar properties on a grand scale? It's a fascinating question topology raises.
These properties of space are wild enough. But then you add time.
Ah, yes. Now we get into Einstein's territory, the really radical idea of time as a fourth dimension.
We usually think 3 dimensions, right? Length, width, height.
That's how we locate things in space. But an event doesn't just happen somewhere, it happens sometime. To fully pinpoint an event, you need that fourth coordinate, time.
Like knowing the address of a house isn't enough. You need to know when something happened there.
Kind of, yeah. The key insight from physics, particularly relativity, is to treat time mathematically as a dimension, similar to the spatial ones. Even though our experience is different, we can move back and forth in space, but generally only forward in time.
And this leads to the concept of world lines.
Yes, a world line is the path an object traces through this four-dimensional space-time. Imagine it like a continuous line mapping an object's existence from its beginning event to its end event. Everything has a world line.
Okay, so if space and time are linked like this, how do you measure the distance between two events in space-time? It can't just be meters or seconds?
No, it's a combined measure. It's basically a generalization of the Pythagorean theorem we use for distance in 2D or 3D space.
A plus BIA CCS.
Right. For space-time, you combine the spatial separation, distance in meters, say, and the temporal separation, time in seconds. But, crucially, you have to make the units comparable. You usually convert the time interval into a distance unit using the speed of light, like light seconds.
Okay, so you combine space distance and time distance.
But here's where it gets really cool and connects back to those imaginary numbers we talked about.
I comes back.
It does. The mathematician Hermann Minkowski, who helped formalize Einstein's ideas, realized that the math for the space-time interval works out perfectly if you treat the time coordinate as if it were multiplied by I, the square root of -1.
Why does that help?
Because when you square an imaginary number, you get a negative result. In the generalized Pythagorean theorem for space-time, the squared time interval effectively gets subtracted from the squared spatial interval, or vice versa, depending on convention. This minus sign is essential for the geometry of space-time.
Whoa. So those imaginary numbers aren't just a mathematical trick for treasure hunts. They're actually built into the fabric of space-time.
That's the profound insight. They seem to be fundamental to describing the geometry of our reality.
Okay, mind officially blown again.
And here's the kicker. This space-time interval, calculated this way, is invariant. Meaning it's the same for all observers, no matter how they are moving relative to the events. Someone standing still might measure the spatial distance and the time gap between two events differently than someone zooming past in a spaceship.
But when they both calculate the space-time interval using this imaginary time formula,
They get the exact same number. That invariance is a cornerstone of relativity. As Gamow puts it, changing your motion is like performing a rotation in this four-dimensional space-time, mixing space and time coordinates but keeping the overall interval constant.
so this constant interval links space, time, and c. The speed of light must be crucial here too, right?
Absolutely central. Gamow really emphasizes the unique status of c, the speed of light. He calls it a fundamental constant, always the same, regardless of human initiative or physical circumstances. It's the only velocity known to have that kind of absolute universal quality.
People tried to measure it early on, didn't they? Galileo with lanterns?
Yeah, Galileo's attempt was probably too crude, but later astronomers like Ole Romer got a decent estimate by observing the timing of Jupiter's moons eclipsing. As Jupiter got further away, the eclipses seemed to happen later, suggesting light took time to cross the extra distance.
That's very close.
Very. But the experiment that really shook things up was the Michelson-Morley experiment in the 1880s.
What were they trying to do?
They were trying to detect the luminiferous ether. Back then, physicists figured light waves, like sound waves or water waves, needed something to travel through. They imagined space was filled with this invisible, undetectable ether.
The cosmic jello again.
Kinda, yeah. And if Earth is moving through this ether as it orbits the sun, then the speed of light measured along the direction of motion should be different from the speed measured across the direction of motion, like swimming with or against a current versus swimming across it.
Makes sense. So they built a super sensitive device to measure this difference.
Exactly, an interferometer using mirrors and beams of light. They expected to see a shift in the light patterns as they rotated the apparatus relative to Earth's presumed motion through the ether.
And what happened?
Nothing. Absolutely nothing. They couldn't detect any difference in the speed of light, no matter the direction or time of year. No sign of the ether wind.
That must have been incredibly confusing. A failed experiment.
It was seen as a failure initially, but it turned out to be one of the most important null results in history. The huge insight was, maybe there is no ether. Maybe the speed of light really is constant for all observers, regardless of their motion.
Which is exactly what Einstein built his theory of special relativity on.
Precisely. The failure of Michelson-Morley paved the way for Einstein's revolution.
Okay, so we have this four-dimensional spacetime, constant speed of light. Where does gravity fit in? Is it still a force pulling things?
Not according to Einstein's general relativity. This connects back to our earlier chat about curved space. Einstein's big idea was that gravity isn't a force acting across distance. It's a manifestation of the curvature of space-time itself.
Mass and energy warp spacetime.
Exactly. Massive objects literally bend the geometry of space-time around them. And what we perceive as gravity is just objects following the straightest possible paths, geodesics, through that curved geometry.
Like the bowling ball, the rubber sheet analogy.
That's the common picture, yeah, though it's hard to visualize in 4D. Gamow discusses the crucial test Einstein proposed for this wild idea.
Measuring starlight bending around the sun.
Right. If space-time is curved near the massive sun, then starlight passing close by should follow that curve, appearing slightly deflected from its usual position. You could only measure this during a total solar eclipse when the sun's glare is blocked.
And did they do it?
Yes. In 1919, Sir Arthur Eddington led expeditions that observed the eclipse. They measured the positions of stars near the sun's edge and found
They were deflected.
they were deflected, and by almost exactly the amount predicted by Einstein's general relativity. It was a huge triumph and strong evidence that gravity really is about the curvature of space-time.
Wow. So gravity is geometry.
That was the revolutionary insight.
And you can tell a space is curved by measuring things like triangles, right?
Exactly. In flat Euclidean space, a triangle's angles always add up to 180 degrees. But on a curved surface, that changes.
More than 180 on a sphere.
Right, positively curved space.
Right.
Less than 180 on a saddle-shaped, negatively curved space. Gamow includes a table suggesting that measuring the geometry of huge cosmic triangles could, in principle, tell us about the overall curvature of the universe, whether it's flat and infinite, positively curved and finite, closed like a sphere's surface, or negatively curved and infinite.
Incredible. We've gone from counting sand grains and grappling with different sizes of infinity through this bizarre curved spacetime where imaginary numbers are real. Okay, now let's change direction completely. Let's descend into the micro world, the structure of matter.
Right. Gamow starts this part pretty relatably, thinking about analyzing something complex, like clam chowder. You break it down. Clams, potatoes, milk, then chemical compounds, then ultimately elements.
And the ancient Greeks had ideas about the fundamental bits, didn't they?
Yeah.
Democritus and his indivisible atoms.
Yeah, or Empedocles with his 4 elements, earth, water, air, and fire. He actually tried to explain stuff with them, like plants growing by absorbing earth and water, or metals forming from earth and fire mixing.
Seems quaint now.
Well, yeah. Modern chemistry showed there were way more than 4 basic substances. Gamow notes 92 naturally occurring elements, each made of unique atoms, the smallest bit that still has the chemical properties of that element.
And scientists started getting handles on how small these atoms were
Yeah.
and that they moved.
Right. Simple experiments like putting a drop of oil on water and seeing how far it spread gave rough estimates of atomic size. Other experiments measuring how fast metal vapor atoms escaped a furnace showed they were definitely in constant energetic motion.
But actually seeing them was tough.
Incredibly tough. Atoms are way smaller than the wavelength of visible light, so you can't just see them with a normal microscope. Gamow mentions early atomic photography, using other techniques, showing these hugely magnified images of molecules, just hinting at the scale.
The real breakthrough, though, was realizing atoms weren't the end of the line. They could be dissected further.
Exactly. People had fanciful ideas first, like atoms having specific geometric shapes that let them hook together. But the first real discovery cracking the atom open was J.J. Thomson finding the electron in the late 1800s.
This tiny, negatively charged particle?
Yep, and much, much lighter than the whole atom. Thomson proposed his plum pudding model, a sort of blob of positive charge making up most of the atom's bulk, with these little negative electrons embedded in it like raisins in a cake.
Like a fuzzy positive cloud with electrons stuck in it?
Pretty much, but that model didn't survive long thanks to Ernest Rutherford.
His scattering experiments.
Yeah, those were absolutely pivotal. He fired alpha particles, which are positively charged, at a very thin sheet of gold foil. According to the plum pudding model, they should have mostly gone straight through, maybe getting slightly deflected.
But that's not what happened.
Most did go straight through, but amazingly, a few were deflected at huge angles, and some even bounced almost straight back.
Whoa! Like firing cannonballs at tissue paper and having some bounce back?
Rutherford himself used that analogy. The only way to explain it, the huge insight, was that the atom's positive charge and almost all its mass weren't spread out at all. They were concentrated in an incredibly tiny, dense core at the center, the nucleus.
So the atom is mostly empty space.
Vastly empty space with a tiny, heavy nucleus and electrons orbiting somewhere outside. This nuclear model was revolutionary.
And it helped make sense of things like the periodic table, how elements behave chemically.
Exactly. The table organizes elements by their properties, and those properties depend on how the electrons arrange themselves in shells or energy levels around that central nucleus.
It also explains how atoms bond together, right? Like making salt.
Yeah, Gamow shows sodium chloride. A sodium atom has one electron in its outer shell that it gives up easily, becoming a positive ion. Chlorine is happy to grab an extra electron to fill its outer shell, becoming negative. Then the positive sodium and negative chlorine ions stick together because of an electrical attraction, ionic bonding.
Okay, so atoms have a nucleus and electrons. But is that the end? Are those the fundamental bits?
The search goes deeper. This takes us into modern alchemy, as Gamow calls it. People had earlier ideas, like Prout thinking everything was made of hydrogen, but that didn't quite work out with atomic weights. The question remained, what are the true elementary particles?
Inside the nucleus, they found protons, positive charge, and neutrons, no charge. But the particle zoo kept expanding.
A really wild discovery was the positron, a positively charged electron. It was the first piece of antimatter found. Yeah. And when a positron meets an electron, they annihilate each other completely. Poof. Their mass converts entirely into energy, usually gamma rays, and the reverse can happen too. Energy can create an electron-positron pair.
EMCA in action.
Directly. It was a massive insight into that mass-energy connection.
And then there were those sneaky neutrinos.
Oh, the neutrinos. Gamow calls them energy thieves. They came about because of a puzzle in beta decay, a type of radioactivity where a nucleus spits out an electron. The problem was energy and momentum seemed to be missing after the decay.
Like something invisible carried it away.
Exactly. To save the fundamental laws of conservation of energy and momentum, Wolfgang Pauli proposed there must be another particle emitted, one with no charge and almost no mass, that interacts so weakly it just flies off undetected, carrying the missing energy.
The neutrino.
The neutrino. Its existence was debated for decades before it was finally detected experimentally. Another fundamental piece slotted into place.
So the book shows this chart of the particles known then nucleons, protons and neutrons, electrons, positive, negative, neutrinos, and things called mesons, and asks, are these the final indivisible things?
A question physicists are still asking today, really. But Gamow then focuses on what holds the nucleus itself together. All those positive protons should be repelling each other fiercely, right?
Yeah, electric repulsion. Why doesn't the nucleus fly apart?
Because there's another force, much stronger at short distances, called the strong nuclear force. It acts between protons and neutrons, nucleons, binding them together. Gamow uses the analogy of sardines packed tightly in a can. The strong force is like the can walls, overpowering the repulsion between the sardines.
So it's a balance between the strong force pulling together and the electric force pushing apart.
Exactly. And that balance determines whether a nucleus is stable or unstable. This understanding of nuclear forces was a fundamental insight.
And when that balance gets upset, you get things like fission and fusion.
Right. Fission is when a heavy nucleus, like uranium, gets destabilized and splits into smaller pieces, releasing a huge amount of energy because the pieces are more tightly bound than the original. That's nuclear power in bombs.
And fusion.
Fusion is the opposite, jamming light nuclei together, like hydrogen isotopes, to make a heavier one, like helium. This releases even more energy per pound because helium is extremely tightly bound. That's what powers the sun and stars. Much more potent than chemical energy from burning stuff.
And radioactivity, discovered by Becquerel, is just heavy nuclei spontaneously falling apart over time.
Yep, unstable nuclei naturally decaying towards a more stable state, spitting out particles, alpha, beta, or energy gamma rays in the process. Natural transmutation of elements.
Gamow also mentions the tools they used back then, right? Like cloud chambers.
Yeah, Wilson's cloud chamber was amazing. It made the invisible paths of these particles visible as tiny trails of mist. You could literally see particle interactions and decays. And he mentions the big electrostatic generators, Van de Graaff generators, used as atom smashers to accelerate particles and probe nuclei. The photos in the book showing particle tracks are really cool.
Wow. Okay, we've really covered a lot of ground from this one book. From just mind-bogglingly huge numbers and the strangeness of infinity and imaginary numbers.
Through the weirdness of curved space and Einstein space-time, where time is a dimension.
All the way down to the particles inside the atom and the forces holding them together. It's quite a journey.
It really is. And Gamow just had this incredible gift for explaining these incredibly complex, often totally counterintuitive ideas in a way that felt like an exciting adventure, you know?
Yeah. And it's striking how concepts that started out seeming purely abstract or mathematical, even
Imaginary.
or a fourth dimension, turned out to be absolutely essential for actually describing physical reality. That feels like a really key takeaway from the science of that era he captured so well.
Definitely. Seeing the universe through that mid-20th century lens is fascinating too. Their understanding was exploding, but there were still so many huge questions, so many speculations, as the title says.
Makes you think, doesn't it? Given how much more our understanding has exploded since 1961 when this was last revised.
Oh, massively.
What ideas that seem really speculative today in cosmology, particle physics, whatever might turn out to be accepted facts, maybe even foundational ideas 50 or 60 years from now?
That's a great question. What surprises about infinity or the nature of space or the ultimate building blocks of matter might still be waiting out there for us to figure out.
Something to ponder.